Just continuing on with a wee bit about equilibrium. So this is the last kind of boring enough bit. Then we're into the good old calculations. So bear with it. So this thing's known as the equilibrium constant. An equilibrium constant, or Kc, so big K, small c. So big K, small c. Use it as a subscript. Tells us how far a reaction has gone, but not how fast. So how far a reaction has gone to completion. So they'll generally say such a yield is 17% yield, and those generally the yield you get with your ammonia reaction. How far a reaction doesn't tell you how quickly it's gone there. So this is the big thing with Kc. The only thing that affects it is temperature. So it's temperature dependent. So provided temperature remains constant, there's a simple mathematical relationship between the concentration of the reactants and the products in an equilibrium mixture. But just remember equilibrium. Equilibrium means when the rate of the forward reaction equals the rate of the reverse reaction. That's all you've got to say for definition. When the rate of the forward reaction equals the rate of the reverse reaction. And that's when the graph begins to flatten out. Dynamic equilibrium, because there's reactions continually occurring. Products are forming reactants and reactants are forming products at the same rate. It's like your man in the treadmill. So they came up with, say we had a general equation, a small a, big A. These are small letters in front of it, so that's like a 2 or a 3. That's what that's denoting. The equilibrium constant, which is your Kc, is found by your concentration of your products over your reactants. Now these are square brackets. You used to use square brackets as well because that means the concentration in moles per litre. So once we get into the calculations, we'll have to get the concentration in moles per litre. So Kc is the concentration of the products over the reactants. Products, remember what's formed in your reaction. Those on the right hand side, your reactants, those on the left hand side. So in this case, it's C to the power of whatever number's in front of it, times being multiplied by big D to the power of whatever the number in front of it, over your reactants, big A to the power of A plus big B to the power of B. And that's Kc, your equilibrium constant. If we go back to the Haber process where they make ammonia used in fertilizers and explosives, if I wanted to write the equilibrium constant here, it's concentration of your products. Remember your square brackets just means in moles per litre. Once you get into the calculations, this will all come together lovely. The next video. Products over your reactants. So then you fill that in, the products, what's on the right hand side, NH3 to the power of 2. So once we get a figure of moles per litre of ammonia, we square times, or over, our reactants, N2, no number in front of it, it's to the power of 1, times H2 to the power of 3. And we'll have figures here, or we'll work out figures here, and we'll get an equilibrium value. Now, when we get a value, if the value is bigger than 1, because the numerator is bigger than the denominator, if the value is bigger than 1, that means more products being formed. The bigger the value, the greater the extent the products are being formed. And what they say there is equilibrium is on the right hand side. When they say that equilibrium is on the right hand side, they're forming more products. If the value is less than 1, that's because the values down here below the line are bigger. So if the value is less than 1, we're forming more reactants. So equilibrium is very much on the left hand side. So in industry, you'd want equilibrium very much to be on the right hand side. You want a very large value of Kc, and the only thing that affects that Kc is that it's temperature dependent. So when they quote a value of Kc, they'll often give the reaction and they'll say Kc is equal to such and such at, say, 350 Kelvin. So you'll often see a temperature at the end of these equations because it's temperature dependent. That often comes up. What's the only thing that affects Kc? It's temperature dependent. So every particular reaction has its own value for Kc. At a particular temperature, the reaction takes place. And the larger the value of Kc, i.e. if Kc is bigger than 1, the greater the extent equilibrium is pushed towards the products. The greater the extent equilibrium is on the right hand side. Equilibrium lies on the right hand side, and that'll all come together when we look at Le Chatelier. And a small value of Kc, that means if the value is less than 1, if we get a fraction, a third is 0.33, very little reactants have been converted to products. equilibrium lies on the left hand side. So when I say it lies on the left hand side, we're on our reactants. If it lies on the right hand side, we're forming our products. And then we'll look at just writing a few more KCs, and we'll get into the calculations then. So write equilibrium constant for the following. Here they give you the equations. You can see the arrows are drawn correctly, indicating a reversible reaction. And I wanted to write Kc here. It's products over your reactants. Your products there, NO2, and don't forget, stick to the power of 2 over N2O4. And we will be getting figures for these, so there's two types of calculations. Kc here, I just wrote it the other way about. The products in this case is me nitrogen and hydrogen. So nitrogen times, that's what the wee dot is, H2 to the power of 3. Don't forget your square brackets, because that's mean moles per litre, over NH3 squared. And then for this last one, Kc products NO2 squared over reactants NO to the power of 2 times O2. So the big thing I want you to take from these two short videos is your definition of equilibrium. So when the rate of the forward reaction equals the rate of the reverse reaction, you might say then, why is it described as dynamic equilibrium? There are reactions continually occurring. Reactants are forming products at the same rate as products forming reactants. And the last one, reversible reaction, a reaction that can take place in either direction. Then to know how to find your Kc, and that it's products over reactants, and to know that it's temperature dependent. If you know that, you'll be very well set up. Right, I'll read your textbook now actually as well. So just chapter 18, when you understand the chemistry, if you're in Chemistry Live, chapter 17, and if you go through the first few pages until you get to the calculations in the yellow bit.